What we're going to start with is a two-tailed hypothesis test. I want to make sure you know the pieces and parts that you need to perform a hypothesis test and that you know what your answer means when you get out to the end. A certain steel company produces ingots that are advertised to crack only 20% of the time. A metallurgist working for the company randomly samples 60 ingots and finds 13 cracked. Does she have evidence the actual crack rate is different than the advertised rate? The first word you need is evidence. Whenever you are asked, is there evidence, you know that you're going to do a hypothesis test. After we find our evidence, we're going to go through our question and dig out our numbers. We have the advertised or accepted rate of 20%, and then we also have the 60 and the 13. Let's see, P, or the accepted rate, is 0.2, X is 13, N is 60. 13 divided by 60 will give us our P hat, which is 0.217. So I have the data that I need to get going, but we know that there's a hurdle, my assumptions and conditions. You know that your first is independence. I assume each ingot is independent. When might the ingots not be independent is if they all came from the same batch. And that's the kind of stuff that you'll tackle when you get into college level stats, is what do you do when the outcomes are dependent. So I assume each ingot is independent. Does the question state randomly? Yes, the question states randomly. The question states randomness. So you notice how we're starting to shorthand our assumptions and conditions. Just don't go too far. 13 is greater than 10, and 13, 50, 47 is greater than 10, so pass-fail is working. And the last one is, I assume 60 ingots is less than 10% of all ingots. I can proceed. I think I spelled that wrong. Here's my normal model, 0.2, because that's my assumed value, and then my standard deviation, which would be 0.2 times 0.8 over n, which is 60. Now that I've passed my assumptions and conditions, I get to the new part. We would have moved into a confidence interval in the past. Now we're going to do a hypothesis test. My null hypothesis is that the proportion of cracked ingots is actually 20%. My alternative hypothesis will be that the proportion of cracked ingots is not 20%. The reason I would go with is not is because the questions prompted me to say, is the actual crack rate different? So different means not equal to. The question will always tell you which way to go. In class, as we were experimenting with these, we would ask ourselves which way would make more sense. Just know that in the actual questions, you will be prompted which way to go. So my null hypothesis is that I'm at 20%. My alternative hypothesis is that I am not at 20%. So I'm going to do my normal model, happy normal model, good old 0.2. And if we do our math, which I'm going to ask you to do while I'm doing it on my calculator, you will get a standard deviation. So the standard deviation of p hat is 0.0516. So that means one standard deviation would be 0.2516, and going the other way, it would be 0.1484. Because I'm not equal to, I want both of these areas. I'm going to add both of these up. You're like, great, Miss Meyer, how do we do that? Well, how do we compare any proportions on a normal model? We crack out the good old z-score. I can only look at two values at a time, and what you're going to see in the textbook and what you may see in questions is p hat and p naught. P naught goes with h naught. So how come they don't just say p hat minus p? Trying for clarity, knowing that p naught matches h naught, that's the best I can give you. And we know that our p's are the actual p's. We'll talk about it in class. So p hat, which in our case is 0.217, minus 0.2, all divided by the standard deviation, gives us a z-score. Let's see if you can do this faster than me. 0.217 minus 0.2 divided by 0.0516. Did you remember to use your parentheses? 0.329. Is 0.329 this probability? 0.329 is not this probability. 0.329 is our z-score. So what we would do is second VAR's normal CDF. We would go from 0.329 to infinity, or 10 to the 99 with 0 and 1. And we get the actual probability that z is greater than 0.329 to be 0.37. Here's the problem. The probability that I'm above is 0.37. If the probability that I'm above is 0.37, can you guess what the probability is I am below? That's also going to be 0.37. So what we wind up having to do is multiplying by 2. Because this is a two-tailed test, we're going to multiply the probability by 2. That winds up giving us a probability of 74%. This is where we get our sentence now. A p-value of 0.74 means if the true proportion of cracked ingots were 20%, I would see the observed cracked ingots 75 times out of 100 with a p-value. So now we got to get to this, large or small. What do you think 74% is? I'm glad you said large. So large, small goes with reject. That means large goes with I fail to reject. The null hypothesis. I have evidence. The crack rate is, now this is going to bug you, but go with it, not different than 20%. How's that for squishy language? And just in case you wanted to check it with your calculator, there's my p-value, 0.7468856. What we need to talk about now is alpha. Alpha is a number that you need to declare at the beginning of a problem that gives you your threshold for rejecting or failing to reject. Alpha, as we discussed in class, is the line that says, yes, from here over, I think the information is legit, and if it's beyond this point, I don't think it is. A large city's DMV claims 80% of candidates pass the driving test. A newspaper randomly samples 90 driving-age teenagers, and only 67 passed. We're going to assume all conditions are met. Is there evidence? And as soon as you see that word, you should perk up. Yay, hypothesis test. The pass rate for driving-age teenagers is less than the DMV reported. Well, if my assumptions and conditions are passed, then I don't need to worry about that. Instead, I'm going to start grabbing my data. What's P? It's 0.8. What's X? 67. What's N? It's 90. What's P hat? 0.744. What's the standard deviation of P hat? No, seriously, do it. .042 is your standard deviation of P hat. P goes in the middle. P hat, 0.744, is over here. This is the p-value I will be looking for because of the less than prompt. What is the probability that we are less than 0.744%? Here's where alpha kicks in. Because alpha is not given to us, we may choose. Our alpha levels correspond to our confidence interval levels. I either have a 1% alpha level, which is a 99% confidence interval, a 5% alpha, which is a 95% confidence interval, or a 10% alpha, which is a 90% confidence interval. What we're going to do is we're going to pick good old 5%. And that goes, when we do our assumptions and conditions, it will fit in right there. I will use alpha equals 0.05. So what I'm saying is, if this number is bigger than 0.05, it is so large. And if it is less than 0.05, it is so small. So that's my threshold, is at 0.05. Now we get to do what we always do, which is our happy z-score. Let's see, we've got 0.744 minus 0.8, all divided by 0.042. Let's see what we get. I'm at negative 1.33. Second bars to negative infinity, so negative 10 to the 99, all the way up to negative 1.3301, and what we get is a p-value, so the probability that z is less than negative 1.33 is 0.92, because we want to go to those 3 decimal places. My alpha level is 0.05. So 0.05 is about right there. Since my p-value takes me to 0.092, that's north of 0.05, I would say a p-value of, see if you can finish it before me. the true proportion, not the proportion, then the observed proportion would be seen, let's see, 92 times in 10, 100, 1,000, in 1,000, with a p-value. Now remember, we think about alpha. Since 0.09 is greater than 0.05, we're going to call that large. With a p-value so large, I fail to reject the null hypothesis. I have evidence drivers are passing at the 80% rate. Now, I want you to think about alpha, and I want you to think about our p-value. Look at alpha, look at our p-value, look at alpha, look at your choices. You've got 3 choices. Look at your p-value. I picked 0.05, and when I picked up an alpha of 0.05, I failed to reject my null hypothesis. What could I do if I wanted to reject my null hypothesis? If I wanted to say this was so small, if I want to say this is so small, my alpha needs to be larger. The only alpha that is larger is 0.10. This is called p-hacking. Should totally look it up. It gets you onto that 538 website, and it's kind of fun stuff. If you look into p-hacking, when you get a result that is close to one of your alpha levels, you can just kind of adjust your alpha levels and force your outcome to come a certain way. If I had an alpha level of 0.10, instead of saying I have a p-value so large, I would say I have a p-value so small, I reject the null hypothesis. I have evidence drivers are passing less than 80%. Think about how a driver's ed program might want to p-hack that data. Maybe they want to reject the null hypothesis so they could advertise that their driving school would help you pass the test faster. That, of course, is unethical. You always declare your alpha before you run your analysis. Always. And anyway, we don't know what would make this pass rate change. Again, if you wanted to check with your calculator, there's my z-score, my p-hat. The conversation we'll have in class is why this says regular p and not p-naught. If you have any questions, feel free to text me.